Hello everyone, welcome to Math 1326 Exam 1 Review. These are the list of topics that we'll be going over today, and you will see that I know for those in PLTL I did send a list of topics before. I just want to point out that improper integrals is no more on Exam 1, and limits of a function is on Exam 1, and it was not listed under the previous list of topics. So if y'all want to quickly take a picture of this or anything, go ahead and do so. I'll give everyone maybe like 10 seconds to do that. Okay, I'm going to move on now. So our very first topic is functions. A function is any relation that assigns every element of the first set with exactly one element of the second set. So every single input must have an output for it to qualify as a function. So looking at the picture here on the right, does this qualify as a function? Go ahead and put it in the chat if you think it qualifies as a function. I would say this does not qualify as a function, as you see that C does not have an output S. Also, I'm going to quickly stop sharing and then start sharing again. There's just something doesn't look right here. Sorry about this. Okay. Cool. If you have any questions about functions, go ahead and put in the chat. Moving on to domain. So domain is the set of values of an independent function, and the independent values are the x values and the y values are the dependent values. So to compute the domain of a function, you would base it off of the agreement on domain, which you all can read that is on the slide. Unless otherwise specified, the domain of the function is the largest set of the real number that is a meaningful replacement of the independent variable x. So what is the domain of this function? Go ahead and put it in the chat. Would someone like to unmute and tell me what the domain of this function they think is?
All real numbers?
Yes, that is correct. Thank you for unmuting yourself. Okay, with that, we'll move on to the basic operations of functions. So basic operations of functions is basically taking like two functions to create a new function, or taking like two numbers to create a new number, right? In this case, we'll be thinking of functions. So sum of two functions, which is just adding two functions. So as you can see, the formula here, f plus g of x is equal to f of x plus g of x. And then difference of two functions is subtracting two numbers. Subtracting two functions. And then product of two functions is multiplying two functions. And then division of two functions is basically dividing two functions. Some things that you want to remember is that order does not matter when you're adding functions, but when you're subtracting functions, order does matter. You cannot, if it says the first function minus the second function, you cannot do second function minus the first function and expect the same answer. When you're multiplying functions, it does not matter whether you do first function times the second function, but when you're dividing them, it does matter if you do the first function divided by the second and the second function divided by the first. So that is something you want to be careful of. Going on to the composition of two functions. So composition of two functions is basically denoted by f of g of x, and it's basically f of g of x. So these are some of the formulas that you can kind of remember or look into while doing compositions. And something you want to remember with compositions again is that f of g of x is not equal to g of f of x. With that, we will move on to the basic differentiation rules. So these are the lists of basic differentiation rules. The first one is the derivative of a constant. So if you have a derivative of 2, if you're trying to find the derivative of 2, it is just 0. And then the second one is power rule, which is the first basic rule that you learn when you're learning how to take a derivative of a number, or sorry, how to take derivative of a function. And then for the fifth one is your product rule, and then your sixth one is your quotient rule. So for your product rule, it doesn't matter if you take the derivative of the first function first times the second function plus derivative of the second function times the first function. But for quotient rule, it does matter that you start with the derivative of the numerator first times the denominator subtracted by the derivative of the denominator times the numerator divided by denominator squared. So make sure you remember the order there. And then here down here for 8b, it's just a chain rule with an exponential function. Something that I always get confused is like taking the integral of an exponential function and trying to differentiate an exponential function. So make sure you're multiplying by the derivative of the exponent, not dividing. And with that, we will move on to derivative of the function using log rules. So you're going to be given derivatives that have a natural log, and then you can often simplify it using these logarithmic properties to simplify the function and then to find the derivative of that. So in this case, the function natural log of 7x times 3x plus 5 times 3x squared plus 1 whole to the exponent of 5. You can see that you can simplify it using the log rules first, and then you can take the derivative to calculate, and then you can take the derivative, and then it's much easier to take the derivative of it once you've simplified it using logarithmic properties. Moving on to the second derivative test. So these are the steps that you would use to find the relative maximum or minimum of a function. So you would start by finding the first derivative and setting it equal to 0 to find critical numbers. When you find the critical numbers, you want to make sure that it is within the domain of the function, and those that are not within the domain of the function should not be plugged into the second derivative to determine if there is a local min or max at that number, because it just does not even exist on the graph. So your step 2 would be to plug in your critical number into the second derivative, and then if it is positive, then there's a relative minimum at that critical point, and if it's negative, then there's a relative maximum, and the test fails if it's equal to 0. And to find the y value of the critical point, because your x value is going to be your critical number, so to find the y value, you would plug your critical number back into the original function that was given, not into the second derivative nor the first derivative. So with that, we will move on to an example. So as you can see, our function is x cubed plus 3x squared minus 9x plus 4. So first, I found the first derivative and found the critical numbers were x equals -3 and x equals 1. And then I found the second derivative, and then I plugged in -3 and -1. And since when I plugged in -3, I got -12, which is less than 0. I concluded that there's a local max. And then when I plugged in -1, I got a positive number. Sometimes you might have like longer equations or like complicated functions, and you don't even have to solve the entire way. Just determine what the final like sign of the final answer is going to be. So if it's positive or negative, and that way you can like see if it's a local max or a min. So when you plug in -1, you get 12, which is greater than 0, so it's a local min. So if I had to find what's the y value or the critical point, so I would plug -3 back into the original equation to find the y value for that point. And then I would plug in, I'm sorry, I shouldn't use -1 here. It should have been +1. I just wrote it wrong, but I still did plug in +1. I'm sorry about that. So yeah, you should plug in +1 back into the original equation to find the y value. Yeah, I did plug in +1. I just wrote it wrong here. Sorry about that. And then moving on to concavity and inflection points. So to determine whether a function is concave up or concave down in a certain region, you would find the second derivative, set it equal to 0, and find you would find the x values of the point of inflection. These points are not your critical numbers. That is something you don't want to get confused with. These are the points where the graph changes its concavity. That's your inflection points. So, and then you would use a number line to determine the concavity. And I will, when I'm walking through the example, I will like kind of further go into what the number line is. And if the second derivative is greater than 0, then the graph is concave down. And if the second derivative is less than 0, then the graph is concave up. So going over the example here on the right. So when you set the second derivative equal to 0, you get x equals -1. And this is what I do. I just put it on a number line like this, and then I just put -1. And then I take a number to the left of -1, in this case, like let's say -2, and I plug it into the second derivative, and I see that it's less than 0. So that's why I would say it's concave down. And then I would take any number greater than -1, like let's say 0, and then I plug it into the second derivative, and I see that it's greater than 0, so the graph is concave up. Wait, second derivative is greater than 0. Okay, I made a mistake writing this. 1 second. Okay, sorry about that. Okay, going back to if the second derivative is greater than 0, the graph is concave up. If it's less than 0, it's concave down. So here the graph is concave down from -∞ to -1, and from -1 to infinity, it's concave up. And to find the point of inflection, I would just plug -1 back into the original equation, and I would get 15. So that is where is my point of inflection. Okay, I'm really sorry about this. I'm going to repeat it again. The second derivative, when you plug the number into the second derivative, if it's greater than 0, it's concave up. And if it's less than 0, it's concave down. Okay, moving on to limit of a function. So when you get a question, you would first plug x equals a into the function, and then you would see that if you get a non-zero number, then we just say the limit of the function is at x equals a. But if you get a 0 in the numerator and a non-zero value in the denominator, then the limit is also at x equals a. But if you get a 0 in the denominator with a non-zero value in the numerator, then the limit is undefined. But if you get any indeterminate form, such as 0 over 0 or infinity over infinity, we would do like traditional techniques first. We would try to factor the numerator or the denominator. We would try to simplify it. We would try to multiply by a binomial conjugate, or try to do something to simplify the equation down to a point where we can kind of try to plug a back in to see that if we can like plug a back in to see if we can find the limit of the function. But if none of those work, then we use the L'Hopital's rule. So for this, you would use the equation up here. You'd use the formula up there, which is basically that you take the derivative of the numerator, you take the derivative of the denominator, and that way it simplifies it, and then you would plug a back in, and then if you see that it's still giving you indeterminate form, you can keep doing that until you are able to get rid of that form and you're able to end up with an answer. So it's okay to like take the derivative multiple times of the numerator and the denominator. One thing you want to remember is that if you're taking the derivative of the numerator, you want to take the derivative of the denominator as well. So you want to do both when you're doing it. And this must be done after you try to find the limit using traditional techniques. So here's an example where I got the infinity over infinity. So that's why I try to take the derivative, and then when I took the derivative of the numerator, it simplified to 2. When I took the derivative of the denominator, it simplified to 3e to the x. And then I was able to get 0 when I solved it further. So with that, I'll move on to indefinite integral. So these are the basic integration formulas. And the last one here was the one I was talking about that always confuses me when I'm taking the derivative, is that when you're taking the derivative of e to the 8 times x, it's e to the 8 times x times a, but here it's divided by a. And also you want to remember that if it's not a definite integral, right, if it's an indefinite integral, you want to put c. So basically indefinite integrals are the antiderivatives, and there are two antiderivatives of the same function and they differ by a constant. So that's why we put plus c when we don't have like bounds for the integral, saying that, okay, our integral is going to be within this and this number. So when you're trying to integrate, you would start with the basic integration techniques to find the integral of the function. Let's say that does not work. Then you want to try to like FOIL the function, like multiply the two terms, or divide each term in the numerator by the denominator to get rid of the fraction. Or like you want to try to like move a constant out of the function, like, and what I mean by that is that, like, let's say you have 3x squared plus 2 divided by 2. You want to move the 1/2 outside the integral, so now you only have to integrate 3x squared plus 2. And when I say divide each term in the numerator by the denominator to get rid of the fraction, like let's say you have 3x squared plus 2x squared divided by 3x, then you can just divide 3x squared divided by 3x plus like 2x divided by 3x, and that way you can like simplify further to integrate. And if all those do not work, then you're going to do U substitution or special substitution. So let's look at the two examples on our left. So example 11 is just a basic u substitution problem. Your u is 3 plus ln x, and then you would solve for du, and then you would write your integral in terms of u, replace it with du, and then you would just go ahead and integrate, and then once you've integrated in terms of u, you take the original equation that you set equal to u, replace it in the antiderivative, and that's your answer, and do not forget your plus c. But like, let's say it's not that simple, right? Like you say your u equal to x minus 1, like in example 13, and then you solve for du, and then you plug it back in, but then you still notice that there's an x remaining in the numerator. That is when you want to do special substitution. This is where you would be replacing the u equals something equation in terms, you would be solving for x. So in this case, it would be x equals u plus 1, and then you would plug that in so that you can get everything in your integral in terms of u, so that you can go ahead and solve it. And when you go ahead and solve it, this is what you get as your antiderivative in terms of u, and then you would just plug back in what your u is, which is x minus 1, into the antiderivative. Moving on to the definite integral. So definite integral uses the fundamental theorem of calculus, which basically is that once you find the antiderivative, you want to use the upper and the lower bounds, and then you want to plug in your upper bound first minus your lower bound. So you always want to plug in your upper bound first, and then your lower bound of the integral. So as you can see here, b is your upper bound, a is your lower bound, and this is how you would go about it. So when you have a definite integral, you just want to find the antiderivative of this first, and you don't have to put plus c in this case, and then you would just plug in your upper bound, then you would subtract it from your lower bound. And yes, order does matter here since it's subtraction. So let's look at the simple example on our left. So it's the lower bound here is -1 and the upper bound is 3. So when you integrate this, you get x squared over 2, and then you would plug in 3 first, and then you plug in -1, and then you just solve it, and then you get 4. Moving on to area between, oh wait, before we move on to this, with definite integral as well, you will have to do like u substitution. You will still have to do, like, you would start with basic integration. That doesn't work, you would move on to algebraic simplification. If that doesn't work, then you would move on to u substitution or special substitution, just like you did with the indefinite integral. Except here you have bounds to plug in, and then you don't have to put plus c at the end. Right, so area between curves. So to find the area between curves, you always want to start by sketching a graph. On the next few slides, I have some basic graphs so that we can get like a review of like what graphs look like for different functions. So you want to always sketch the graph first to see like where graphs intersect, or like to find out where you might want to split the integral, and just to like get a better idea of like what part of the graph you're finding the area of. So, and then you would decide if the f of x is like greater than your g of x, or your g of x is greater than your f of x. So you want to see which one is your upper curve, which one is your lower curve. So to do that, what I do is that I pick a number between the two bounds given. Like let's say I'm given -1 to 1. I would pick 0. And then I would plug 0 into f of x, and then I would plug 0 into g of x. And then whichever gives me the greater number, I would say that's the upper curve and the other one is the lower curve. And then you want to always refer to the graph before you set up your integral to see like where to maybe split the integral, or like to see how you want to, how the graphs intersect with each other, so that you know like exactly how to set up your integral. Because sometimes you will have to split the graph at certain points, and to know to do that, you will need to have the graph drawn and know which part of the graph that you're finding the area of. So these are the basic graphs. I'm just going to try to zoom in. Hopefully that works. We're looking at the very left top picture. So you just have like y equals x graph, and then we have a simple parabola, and then we have a x cubed graph, and then a square root graph, and then down here we have x to the 1/3, 1/5, 1/7. So anything 1 divided by an odd number. And then here we have exponential graphs, and then we have a natural log graph, and then we have a negative parabola. And then this just basically talks about how your graph would move, right? If you like stretch the graph, or if you move it up 2 or down 2. So that's just what this talks about. So here on number 9, it's talking about how like you would move the graph to up because it's x squared plus 2. But if it was x plus 2 whole squared, then it just means it's stretching the graph, not really moving it up or down. That's something you want to be careful of. And then here on number 10, it's the same thing, but it's just a negative parabola, and you're moving it down. So with that, we will move on to integration by parts. So for integration by parts, this should be your last resort. Like U substitution doesn't work, basic integration doesn't work, none of those work, so that's why you're doing integration by parts. So this is the formula you would use. uv minus integral of v du. So when you're trying to determine what your u is, you would select it using the logarithmic rule. Sorry, not the logarithmic rule, LAE rule, where L is your logarithmic, A is your algebraic, and E is your exponential function. So let's look at the example down here, where it's based on the LAE rule. I would say that U is X because algebraic comes first before exponential function. But then if I had an ln x here, then ln x would be my u. So I just go ahead and solve for du. Something that I used to mess up a lot was I would set v equal to e to the power of x instead of dv to the power, instead of setting dv equal to e to the power of x. You'll see that here it doesn't matter because your dv and your v are the same. But let's say if it was like some other function instead of just x, or sorry, e to the power of some other function, then matter. So you want to be careful that you're not setting it directly equal to v, where you're setting it dv is equal to that, and then you're integrating it. And then down here, I just set up the equation, which is uv minus v du, and then I just integrated e to the x dx, and then don't forget your plus c again. Moving on to the volume of solid revolution. So down here is the formula that you would use for the volume of solid revolution. for those in PLTL, the PLTL packet does not include pi in the formula. So that's something you want to remember, is that pi is included in the formula. And you would, so let's look at the example to the right. So find the volume of the solid obtained by rotating the region around x-axis given by y equals 1/2 x equals 0, x equals 2. So here you're finding the volume from 0 to 2 of 1/2 x squared, right? So this is how you would set up you'd set up the integral first. And then something that helps me is just removing the pi outside the integral. So I don't have to worry about it until the end. But if you do that, you want to remember to bring your pi down to the final answer. That's something I used to forget. So make sure you're bringing your pi down to the final answer. If you do remove it outside the integral. But here, as you can see, I did not remove it. So you would just go ahead and integrate and then use fundamental theorem of calculus to plug in the numbers, and then you would just solve it. Something that you also want to be careful of that is that some of these integrals can be a little complicated, and when you're doing the math down here, you want to be careful about the positive, the negative signs, and all those things, because it's very easy to get like tricked up or to mess up here, because you're so focused on finding the right integral that you just don't care about the math. And then in those cases, you just like make a small silly mistake and your final answer is just not correct. So that's something you want to be careful of. And then the last topic that we have is the average value function. So this is the formula that you would use to find the average value of function. So let's look at the example. So your function is 3x squared plus 4x plus 5, and it's from 0 to 5. So you would set up your integral in the numerator, and your denominator is basically b minus a. So you would just integrate the numerator, use the fundamental theorem of calculus to plug in the numbers, and then you would just calculate the average of the function. So average of the function is just like any normal number. It can be positive, it can be negative, or it can also be 0. So with that, that is the end of this review. Okay, I hope everyone can see the review packet. And on the left, you should find controls if you need to zoom in or zoom out. So what we'll do is that we'll just go through each question and walk through the problem. And what I will do is I will give you all like 2-3 minutes to do the problem based on how complicated it is, and then we will kind of review the answer, and then if you need to like walk through how to solve the problem, then we will do that too. So for the first question, let me see who's in this breakout room. Okay, so for the first question, actually for this one, I will actually call on people so we can like kind of see like what we think. So okay. Drew, what do you think is the answer to the first one? B. And if you cannot unmute yourself, go ahead and put it in the chat. Do you think it's a function or not a function?
What did you call again?
Wait, what?
Who did you call on? I heard Drew, but I wasn't sure. Okay.
Yes, I did call on you.
B is a function.
That is correct. So next, Tarun, what do you think C is? Is it a function or not a function?
It's not.
That's correct. And it's not a function because there are just so many different outputs. And then Olive. Did I pronounce your name right? Okay. Do you think E is a function or not a function? Oh, okay. You can put it in the chat. That's fine. Yeah, that's right. It is a function. Good job. And back to Drew. Do you think F is a function or not a function? Okay, Drew, can you hear us? Okay, I guess not. Can everyone hear me?
Yeah.
Okay. Okay, Drew, do you want to try F?
That's not a function.
Yes, that's right. Thank you. Okay, for the second one, the domain. Go ahead and take 2 minutes to solve the domain, and then after that, we will kind of come back and share what we got. Okay, does anyone have an answer ready for 2? That is correct. Thank you, Olive. So, did everyone get from 3 to 5, 3 included, union, 5 to infinity? Awesome. I'm going to wait for it to run for a second.
Yeah, I got that. But like, do we always need to write it in interval notation or what?
The question should specify, and if it does not, I would say ask the professor, because I'm pretty sure there'll be professors in the room when you're taking the exam. So I'd say definitely ask the professor, but it should tell you. Like here, I specified to put it in interval form.
Okay.
Good question. Okay, now let's move on to basic operations on functions. So this is basically like the composition of functions that we talked about. And go ahead and solve all of these, and then I'll give you all like again maybe 3 minutes, and then we can go over the answers. So does anyone have any questions before you start on this? Okay, I'm going to take that as a no. Great. So let's take 3 minutes to solve this. And actually, once you finish, put done in the chat so that I know you're done with it. Okay, it's been a little over 3 minutes. So what we'll do is we'll kind of go over the ones that we have the answers to. So, okay, I know these answers are kind of long, so I'm not going to make you guys type it in the chat. So Drew and Tarun, you guys are going to be the ones answering this. So Tarun, can you tell me what you got for A?
Yeah, so I just kind of plugged in the G function into the F function. Yeah. Yeah, is that right so far?
Yeah, you plug in the G function to the F function.
Yeah. So I just plugged in fx plus natural log 3x plus 2 into the into both the x's. So it'd be e to the 3 times that plus 1 plus 5 over 4x plus natural log 3x plus 2.
Okay, that's good. Thank you. And then for g of f of x, I'm just going to kind of talk through this. For this one, you would just do the same thing as a, but you would kind of switch up the equations. So now you would do like 4 times the f of x function plus natural log of 3 times the f of x function again plus 2.
Yeah, I got a bit confused on C and D though. I wasn't too sure to do those.
Okay, yeah, I can walk through those too. So for C, you would do 4 times 4x plus natural log of 3x plus 2 plus natural log of 3x, but in terms of x, it would be 4x plus ln of 3x plus 2 and plus 2. So I know that's a little confusing. So
Oh, okay. So you just plug in G in by itself, basically.
yeah, you're just plugging in g again wherever there is x.
Okay.
And then for D, a little trick is that you take your answer from B, which is g of f of x, and then you plug that into f of x. So whatever you got from B, you plug that in 3 to the power of 3x. You do 3 times the answer from B plus 1 plus 5 divided by the answer from B, if that makes sense. Because you would do g of f of x first, and then you would take that answer and plug it in into f of x.
Okay,
If
so
that
I
makes
just plug in. Yeah, so I just plug in my F function into what I got for A.
sense.
Okay.
Or wait, can you repeat that?
Yeah, so I just plug in like my F function, like for what I got for F of G, basically, like my answer
No,
for
you
A.
would do g of x though, because this one, if you rewrite it, it would be I'm just gonna write over this, be f of g of f of x. So you would do g of x first,
Oh,
right?
yeah.
And then you would plug this into wherever there's x's, like here and here. Does anyone have any questions? Does that make sense, Tarun?
Yeah.
Yeah, I can go over C again. So C is basically, so do you see the x here in g of x? So we would do 4 times this whole thing plus natural log of 3 times this whole thing again plus 2. So it's basically, I'm trying to write it, so it'd be g of x. Does that kind of help? Of course. Okay, then we will move on to the next page. So again, if you need to zoom in, use the zoom in tool on the left to zoom in. And then for 4, it's just basic differentiation, and you would use the product rule. That's my hint. So go ahead and take 2 minutes to quickly solve. Actually, let's do this. We'll take 5 minutes to solve both 4 and 5. And 5 is where you would use log rules to kind of simplify it first and then solve it. So in 5 minutes, we'll check back and see what we got. So do we have any questions before we start? Alrighty, then 5 minutes on the clock and solve both 4 and 5. Okay, let's come back and kind of try to discuss the answers that we got for 4 and 5. So we're going to start with, okay, let me see how long the answer is for 4. Okay, it's a pretty long answer, so I'm not going to have Olive type it in the chat. So this is what we will do. Tarun, we're going to start with you. What'd you get for 4?
Okay, so for 4, I got e to the 2x plus 3 times 4 root x plus 7, and then I just kind of took the derivative of the of the exponent. So that was just, and I applied the product rule. So that was just 2 times 4 to the root x plus 7 plus 2x to the negative a half times 2x plus 3.
Did you say 2x to the negative half?
Yeah, because I did 4, because for 4 root x, to take the derivative of that, I did 4x 4 times x to the half.
Mm-hmm.
Yeah, and I subtracted 1 from a half.
Okay.
Is that right, or?
Wait, let me see, because I got a different answer.
Oh, okay, I might mess up.
No, that is correct. Yeah.
What's up?
No, I said that is correct.
Oh,
Did
okay.
everyone else get the same answer too? Okay, I'm gonna take that as an S. And For 5, did you guys finish working on it yet?
I did, but my answer was like just so long.
Okay, Andreas says and Olive says they're still working on it. So yeah, we'll just give them like maybe another minute. Meanwhile, Tarun, you can just kind of move on to 6 and 7.
Right.
Okay, Tarun, if you like finish the questions, feel free to like keep working on the other ones.
Mm-hmm. Actually a bit confused on 7. Yeah.
Okay, let's see. What are you confused about?
The natural log just kind of threw me off. So would I just rewrite it as like 1 over 3x squared plus 7 over x to the 4th? Or like, so would I just...
Mm-hmm. Good
Oh,
question.
okay.
So for okay, you take the derivative of the numerator first, right? So
Yeah.
you would just use the rule, and you would just do 1 over 3x squared plus 7
Yeah.
times 6.
6.
Yeah.
Yeah.
So it'd just be like 6x over 3x squared plus 7.
Mm-hmm.
And then if you take the derivative of the denominator, it'd just be 4x cubed.
Mm-hmm.
Yeah. Then you kind of like try to work from there.
Okay.
Okay, hello Olive. Can you speak now? Is your mic working? Wait, can everyone hear me?
Yeah.
Okay, good. Okay, we'll start going over number 5 now. Um, Olive, I don't know if you can still speak or not. I can't hear you if you're speaking. Um,
Hello?
yes, we can hear
Oh,
you.
okay. Thank God it worked. Yeah, no, I'm on. I just joined on my other computer, but this one's kind of slow, so I was just spending the last like 5 minutes trying to get it to work.
Oh, okay.
Okay, there we go.
So, okay.
Sorry, which part are we on? I think I missed some.
Um, let's go ahead and see what you got for number 5.
Uh, um, so I'm still kind of working on this one. So would we do it just by like using the log properties to expand it first, and then we take the derivative?
Yes, that is correct.
Okay. So what I have right now is I have ln3 plus ln x to the 5 and then plus ln e to the x squared plus 2 and then minus ln 2x plus 1 to the power of 2.
Okay, that's good. Keep working.
Okay.
I have a question.
Yeah, what's up?
Yeah, so for that one,
Mhm.
number 5,
Mhm.
what I did was that like I kind of just flipped it because it was just kind of the natural log times that, you know what I'm saying? So
No. What do you mean flipped it?
like, so you know how is natural log times that function?
Yeah.
So yeah, I did 1 over all of that, and basically you could just kind of like, you know, flip it after that. So it'd be a 2x plus 1 squared over all of that. And then I took that and I multiplied that by uh, my derivative.
Interesting. I really wonder if you need to do that because that kind of sounds complicated.
Yeah,
Um,
I got a pretty long answer.
what did you get for your answer?
Um, okay, so I got 15x to the fourth, e to the x squared plus 2 plus 2x e to the x squared plus 2 times 3x to the fifth.
Okay, I'm gonna stop you right there.
Yeah.
Okay, I don't think you need to do all of that, and that is not the answer I got.
Yeah.
So I think what you need to do is like you need to use the log rules to kind of separate the numerator from the denominator and kind of like work through that, right? As Olive was talking about. So
Mm-hmm.
you would do ln of 3x to the fifth plus ln e to the x squared plus 2 minus ln of 2x plus 1 whole squared.
Yeah, I think I got something different. I got so after simplifying it, I got the derivative would be 5 over x plus 2x and then minus 4x over 2x plus 1. Or no, minus 4 over 2x plus 1, sorry.
That is the correct answer. Good job.
Okay, so wait, I have a question. So
Yes.
I got like on the middle step, I got ln e to the x squared plus 2. Like, would the ln e always just cancel out, and then we can just bring down the x squared, like bring down the exponent?
Yes.
Okay, thank you.
Yeah, of course. Drew, do you kind of see what I was saying before?
Yeah.
Okay. And after you simplify it like that, you can just start taking the derivative of it.
Yeah, so I just took the so what I do is that I just take the natural log of like each one, like the numerator and the denominator.
Mm-hmm.
And then okay.
Yeah. And Olive, feel free to move on to the next questions. Darun, let me know if you want me to repeat the answer to 5 again.
Yeah, can you?
Yes. So you should get the derivative of that should be 5 over x plus 2x
Mm-hmm.
minus 4 over 2x plus 1.
Okay.
Yep. And let's. Oh,
So sorry.
no, go ahead.
So for number 6, for second derivative test, would I just start by um would I take the derivative of the function and then set it to 0?
Yes. So you take the first derivative, set it equal to 0, find the critical points, and then plug that into the second derivative.
Okay. And then if it's like a positive, it's a minimum, I think.
Yes.
Yeah,
Yes.
I always get that one mixed up.
Yeah, no. It's always, you want to think it's like the opposite. If it's like less than 0, then it's the maximum. If it's greater than 0, it's a minimum. Okay, so for number 6, Tarun, did you get a chance to finish working through it?
No. Yes. No, I just got my first derivative, and yeah. How would you say I would go about getting my points from there? Like, I know I need
Just
to just take the derivative of that again. Or
say your first derivative equal to 0,
mm-hmm.
and then solve for x, and that will be your critical number.
Okay. What I got 2x over x squared plus 4.
Yeah, you'd set that
Okay.
equal to 0, and then in this case, you just set the numerator equal to 0.
Okay.
Um, so I think I got the x value, and I'm just wondering when for questions about second derivative, is it just asking if there's like a local min or max, or is it asking for us to like write the exact x and y value?
That's a really good question. Here, just tell me if it's a min or a max. But if it's asking for exact value, right, like an exact point, then on your exam, it should specify whether it's asking for exact point or not. But if it doesn't specify that, then just ask the professor, I would say.
Okay, thank you.
Yeah,
And
of course.
then so after we get the x value, to get the y value, we have to plug it into the
Well,
original.
yes, you would plug it here into natural log of x squared plus 4.
Okay. Okay, thank you.
Yeah, of course. Okay, did someone get an answer for number 6 yet?
I think it would be a local min.
Yes, that's correct. At what point?
1/2. I think that's what I got.
Okay, it should be x equals 0 though.
Oh yeah, the
Because
critical number, yeah.
yeah,
Okay, yeah.
yeah. So 1/2 is what you get when you plug it in.
Yeah.
You're right. Okay, awesome. If you guys could like kind of try to like work through a little bit faster through the other ones, that'd be great because we only have like less than 30 minutes and a few more problems to get through. So what I'm gonna do is like feel free to work through them, and as you work through them, unmute yourself, tell me what the answer is, and I'll just like quickly check if that's what you got. Or if that's what I got too. That's what I meant. So
Alright, so now are we just working on question 7?
yeah. And once you
Okay.
finish question 7, feel free to move on to 8, 9, like kind of work on your own pace.
Okay. Thank you.
Of course. And then once you have an answer to a question, just unmute yourself, tell me where you go.
I'm not 100% sure if this is right or not, but for number 7, I got 0. Would
That
that
is
be
correct.
okay?
Yeah, I got that too.
So I'm just wondering, like, so we just keep taking the derivative until we just get something that's not like infinity over infinity, right?
Yes, that's right.
Okay. I have a question on number 8.
Yes. What's up?
So I got so I think I got the inflection points. I got 1 and -1. I don't know if that's right or not, but so I got the inflection points, 1 and -1, and then I don't what do I'm just kind of confused on what to do after that.
Okay. Um, actually, I realized I'm sharing the wrong file for this one. I think I changed this question because it was like, yeah. Let me just quickly share the other one. I promise all the other questions were the same so far. Don't worry about it. Um, but yeah, that one question is not right. Okay. Let me quickly share the other one. Okay, this is the right one. Yeah, for number 8, please work on this problem. I'm so sorry about it.
No, it's okay.
I was confused.
Wait, did you say you're confused?
Yeah, no, just on the last problem, like number 8.
Yeah, so that's why. Okay, don't worry about that one.
Right, so I have a question on this one, number 8.
Yes,
So I got x equals -1, and
that's
then
right.
so I'm just wondering, like, I know we take 2 points on on both sides of -1, right? So for example,
Mhm.
maybe -2 and 0. So
Correct.
would we plug that into the original, or like which, because we have to, I'm kind of confused on which one to plug it into, the test points.
Yeah, that's a good question. So you would plug it into the second derivative because you're trying to determine if it's concave up or down. But if you want to determine the point, like the inflection point, then you would plug -1 into the original one equation.
Like the y value of the inflection point?
Yes.
Oh, okay, okay. Thank you. So in this case,
Yeah.
we would just
So you
like
would plug -2 and 0 into the second derivative.
okay, okay. Thank you.
Yeah, of course.
Wait, sorry, I got a bit confused. Like, what you said you plug a -1 into the y function for the inflection points, or?
Okay, so once you get the second derivative and you set it equal to 0, you should get x
Yeah,
equals -1.
yeah, yeah, yeah,
And then let's say you want to find the y value, right, for that
yeah.
inflection point, then you would
Hmm.
plug -1 back into the original equation
Yeah,
to find the y value, and you should get 15.
yeah, yeah, yeah,
Does that help?
yeah, yeah.
Okay, good.
Uh,
Wait, I have another question.
Yes, what's up?
So I'm just wondering, so since we got x is -1, you said if it's negative, it's a local max, right?
Because it's -1, it's a local max.
Yeah, I was just wondering, like, if it's negative, it's a max, and if it's positive, it's a minimum.
You can't really determine that using that number though, because that's when you set your second derivative equal to 0. Your maximum and minimums are determined from your critical numbers. That's where you set your first derivative equal to 0.
Oh,
Hmm.
okay. Oh, okay, okay, okay. Thank you.
Yeah, of course.
On number 9, um, so would you say to always like simplify before we try to take the integral? Like, so on number 9, 2,
Wait,
like,
wait, wait. You're like cutting off. Can you repeat it? I'll go on mute. Maybe that'll help.
I'm sorry. No, I think it's just like, uh, I'm wondering, like, on number 9, would you recommend like always simplifying before we try to take the integral? Like, for example, number 9 2 would be. I'm just looking at it, kind of confused. Would we like divide each term by the square root of x before we try to solve it, or?
Yeah, that's a good question. You're still kind of cutting off. But I think I got what you're asking. Are you asking like for number 9, part 1 or part 2?
Part two. Sorry, I think here I can try typing in the chat. I think it's just my
Wait,
my
wait,
connection.
no. It's clear now. So
Okay.
you're just asking if you would divide each term by root x?
Yeah, like before we take the.
Mm-hmm.
Okay, and then how do we know when to use like how do you know like when to use stuff? Something I always mess up. Like I'll try something, but then I'll realize like, oh, we should have done the use substitution.
Yeah, so like let's say if each term is like not separated, right? And you can't really separate it and you have like a binomial in your denominator, right? In that case, you would use u substitution, right? Like for example, if you have x over x squared plus 2, you can't really separate it into x divided by x squared and x divided by plus 2, right?
Mm-hmm.
So that's when you would like have to use sub.
Oh, okay, okay. So just when
Yeah.
you like when you can't really do anything else.
Yeah, and you can't
Okay,
really
thank
set
you.
it. Hmm.
Right. I forgot how to like. So the integral of something like e to the 3x, would that just be the same thing, like e to the 3x, or would we? I forgot the formula for that one.
Like if it's e to the 3x.
I think yeah, like for example, the first part of question nine, like at the end.
Wait, you kind of cut off at the end.
Oh, sorry. Yeah, like at the end of or part one of question nine, there's like e to the 3x.
Wait, are you asking like for part 9? I mean, question 9, part 3?
Oh no, sorry, part one.
You wouldn't use sub, but
Oh
are you
no,
asking?
I'm saying I like there's the e to the 3x at the end. I just forgot how to take the integral of something like to the e.
Oh, okay, yeah. So for that one, you would just do, if it's e to the ax, let's say, then you would do e to the ax times a.
E to the ax times a, so it'd be e to the 3x times 3.
Yeah, that's right.
Okay. Okay, thank you.
Yeah, of course.
Oh wait, I thought it'd be e to the 3x over 3.
Oh yeah, because it's integral, not derivative. See, this is what I was talking about when I like mix up the two. No, you're right. Yeah, sorry about that, Olive. It is e to 3x over 3 because it's integral, not derivative.
Oh, okay, okay. So okay, so integral we divide by the number instead.
Mm-hmm.
Okay,
Yes.
thank you.
Thank you, Tarun.
Oh, you know me.
Okay. Did we like go over what we got for number 8? No, right?
Yeah, I think so, yeah.
I think we did.
Oh, okay. Then never mind. Um, okay, just to confirm, we said that -1 to infinity is concave up and -infinity to -1 is concave down.
Yeah.
Yeah.
And then the inflection point is -115.
You said -1 and 15.
Yes.
Would that
Okay,
be
cool.
the y value?
Yeah, the y value of the inflection point.
Okay. For number 9b, I don't know if
Mm-hmm.
I did this one right. I got 2/5 x to the 5 over 2, then plus 2x to the 3 over 2, and then plus 10x to the 1/2.
That's right, you're just missing plus C.
Oh, okay. Yeah, I always forget that.
Yeah, you don't want to
But
forget C.
oh, sorry.
Oh, I just said you don't want to forget plus C. I think your exams are going to be like free response, so
Mhm.
that's something you want to remember.
Oh yeah. Okay. Okay. Thank you.
Oh, yeah, of course.
Oh, and when we're doing U sub, how do we know like which? So there's like two terms. How do we know which one to use for the U?
Yeah, so you would always pick like it depends. Like for number 3, right? Your
Mm.
you would be x squared plus 2. You kind of want to pick the most complicated one, or you want to pick the one when you take the derivative of will help you get rid of something that's is going to be left in the equation. Like for example, here x is going to be still there, right? So when you take the derivative of x squared plus 2 for du, you get 2x, right? And
Mm-hmm.
you would get when you rearrange your equation, you would get du over 2x. And then you can kind of cancel out the x, and you can kind of get rid of that, and you'll be left with the more simpler integral.
Oh, okay, okay. Okay, I see. Okay, thank you.
Yeah. Okay, we have like 1 more minute, so what I'm gonna do is you guys can like kind of take a picture of this or something, and you must be able you must be able to move to the next slide as well and take a picture of it. Can you guys do that? If you want the questions, you can kind of look over it. Then I'm gonna stop all the breakout rooms. Okay, hello everyone. Thank you for joining the review today. Um, Earlier in the chat, there should be a link to YouTube that would like give you access to this recording and everything. So you guys can refer to like the first part of the review if you want to go over again through that YouTube link. And if you have any other questions, you can contact your tutoring leader or your PLTO leader or your SI leader. So with that, this will be the end of the session. So thank you everyone for joining.
Thanks.
Yeah, of course.